All right, welcome. If you're anything like me, you live in this world of abstract logic, writing code, designing systems. But it's kind of wild to think that underneath every single line of code, there's a physical reality. In this explainer, we're going to tell the origin story of the single most important component in your computer. And it all starts with the most basic problem there is. How do you actually control electricity?
Okay, let's just dive right into that. Before we can even dream of having algorithms or data structures or any of the apps on our phones, we first have to solve this fundamental physics problem. I mean, how do you take the raw, chaotic power of electricity and make it predictable enough to actually perform calculations? How do you get it to think?
Just imagine it for a second. A raw electric current is basically a chaotic mob of electrons. It's a stampede. It's got a ton of energy, but it's just running wild. Now, to make it do something useful, like, run a computer, we can't just let it flow wherever it wants. We've got to bring some order to that chaos. And this, right here, is the crucial point. The zeros and ones that are the building blocks of everything we do in computer science? Well, they have to physically exist inside the machine. And the simplest way to do that is with a switch. Current is flowing, we'll call that a 1, or current is not flowing, and we'll call that a 0. The entire digital world is built on this simple physical command: stop and go.
So how do we do it? How do we build a gatekeeper for this mob of electrons? An electronic bouncer that can check IDs and decide who gets in and who doesn't? Well, the solution, cooked up by some brilliant physicists, is an incredibly ingenious little device called a PN junction.
It all starts with plain old silicon. Scientists figured out how to dope it, which is just a fancy way of saying they mixed in some specific impurities. And this gives us two distinct flavors. You've got P-type silicon, which is full of positively charged holes. You can think of these like empty parking spots just waiting for an electron to pull in. And then you have N-type silicon, which is the opposite. It's got a surplus of free, negatively charged electrons just itching to move.
Now, this is where it gets really clever. When you stick these two types of silicon together, something amazing happens. The free electrons from the N side immediately rush over to fill those empty parking spots on the P side. This little shuffle creates a neutral zone right in the middle, a kind of no man's land where there are no free charges left. And that zone acts as a natural barrier, stopping any more electrons from crossing. That's it. That's our bouncer, instinctively standing guard.
And that structure, that one-way gate for electrons, is the essence of a device you've probably heard of: a diode. Its whole job is to let the electron mob flow in one direction, but not the other.
Okay, so we've got our bouncer, but here's the really cool part. We can actually give this bouncer orders using an external voltage. So let's start by telling it to open the door and let the crowd in. So, this is what's called forward bias. We apply a positive voltage to the P side and a negative voltage to the N side, and this basically pushes both sides toward the middle. The positive voltage shoves the holes and the negative voltage shoves the electrons, pushing them both right toward that barrier. All that pressure just squishes the barrier down to nothing.
And check this out. This shows you exactly what happens. You see the circuit setup, and then that graph, well, it tells the whole story. As soon as you apply just a little bit of forward voltage, that barrier collapses and bam, the current flows. The bouncer has stepped aside, the mob is on the move.
And for us, in the CS world, this is huge. This state, current flowing, is the perfect physical way to represent a logical 1. It's our go signal, it's the on state.
Okay, so our bouncer is great at letting the crowd in, but a good bouncer also needs to know when to lock the doors, right? So what happens if we give him the opposite order?
And that, my friends, is reverse bias. We just flip the battery around, connect positive to the N side and negative to the P side. Now, instead of pushing everything together, the voltage pulls the electrons and holes away from the junction. It makes that barrier, that no man's land, even wider and stronger.
And the effect? It's so simple, but so powerful. The barrier is fortified. The door is locked shut. Absolutely no current can get through. The mob is stopped cold. So there you have it, the other half of the puzzle. This no current state gives us the physical reality of a logical 0. It's our stop signal, the off state. We now have a physical way to represent both 1 times and 0.
So we've got our bouncer, our diode that can follow go and stop orders, but the real magic, the leap that actually allows computers to think, that happens when we combine these bouncers in a very specific way.
Look, a one-way door is neat, it's useful, but it's not going to create a thinking machine, right? The next big leap, invented by William Shockley back in 1951, changed literally everything.
Instead of just having one p-n junction, they created a sandwich, something like NPN. This amazing little sandwich is a transistor. You can pretty much think of it as two of our bouncers placed back to back, with a super thin layer right in the middle.
And this is the absolute game changer. A transistor isn't just an on or off gate. It is a controllable gate. A tiny little electrical signal sent to that middle P layer, they call it the base, is like a whisper in the bouncer's ear. And that tiny whisper is all it takes to control the massive flow of current from one end side to the other. Think about that. It's not just an on-off switch. It's an on-off switch that you can control with another tiny signal.
And it's this amazing level of control that lets a transistor act as a near-perfect electronic switch. A very small signal flips it between a closed switch where the main current flows free, that's our on state, R1, and an open switch where the current is completely blocked, that's our off state, R0.
And folks, this is the super switch, the thing that powers our entire modern world. It has no moving parts, so it can flip states millions, even billions of times a second. It's so mind-bogglingly small that we can cram billions of them onto a single processor. And these billions of switches, all flipping on and off, are what perform all the logic that makes your computer do what it does.
So it really all boils down to the super simple idea from the source material. Depending on that little control signal, the transistor acts as an open switch and acts as a closed switch. It is the perfect physical manifestation of our binary 0 and 1, a controllable, reliable, and ridiculously fast bouncer for electrons.
It's pretty wild when you think about it, right? From just wanting to tell a mob of electrons stop or go, we created the p-n junction, then the transistor, and from that, well, the entire digital universe. Every time you compile your code, you are orchestrating a symphony for billions of these tiny bouncers. And that just makes you wonder what's going to be the next fundamental switch that changes everything all over again.